samples, what do you get out of it? And here, some pretty pictures. That is that coming out from each of the corners of my indent, there's a little crack that runs out. And then what I've got is a picture, a map of the different components of, in this case, the strain tensor, just laid out as you would in a normal tensor. So here's the strain along the x1 axis, the horizontal axis in here, which is sort of compressive horizontally. You put a crater, an indent into the sample, it's pushing material out sideways, so you get compression pushing back there. You kind of expect you might get some tension up there above, but there's a crack. That's why the crack's there, so the tension goes away. If we look along the x2 direction, so that's going up vertically, again you see a similar thing, but it's all rotated around. Material's getting pushed out top and bottom, that leads to a compression along that axis. In these regions in here, either side, we get a tension, but it's relieved because there's a crack. The shear terms in here, you can see these two colourful lobes in here. If you look at those and apply more circle in your head, you'll see that those are kind of equivalent to what I've got on here. So these are lobes of about 45 degrees in here. So rotate it round and it'll tell you that there's a compression along this axis and actually a tension, because we don't have a crack in this instance here. It's not a cleavage plane. So this all kind of makes sense. Strain levels in here, so it's 200 plus or minus 200 times 10 to the minus 4. We also get the lattice rotations. And here largely you see, so around an axis that's running vertically, on one side of the indent things get pushed out, so there's a lattice rotation off in one sense, and on the other side it's off in the other sense. This field here is looking at things going around the horizontal axis, and so things are sort of moving out this way and that way, above and below the indent. And in this case here, actually you can see, hopefully see just faintly, the in-plane rotations, so rotations about an axis coming out of the board. You can just pick out the rotations either side of the crack that runs out from the indent. Okay. So just one quick other example. This is looking at a very old sample, Indian gallium arsenide, grown on a gallium arsenide substrate. It's been grown, the sample I'm going to pick out here is several tens of nanometers thick. X-ray measurements tell you that the lattice has relaxed, the interface has relaxed a little bit. Okay? Some of that is split strain relaxed away. So there should be dislocations in the system. And then this is looking plan view on the top of that sample, that Indian gallium arsenide film. Again, looking at the strain tensors in here, you can see for strains along, normal strains along this horizontal axis, there are a set of stripes in here, and that corresponds to a set of edge dislocations that are running, buried under that layer, running vertically through here, and locally to them, they relax the strain. There's a similar set that runs horizontally across the sample. Edge components of that relax the strain on the other axis. Okay. You can also see, though, that there's some shear term in there, and that implies actually that there's some screw component to those dislocations as well. There are actually, if you look at the individual dislocations, they're 60-degree dislocations, but you can see it here that actually they're paired up to remove some of the screw-type nature, but to force up the edge-type nature. Again, you see similar things in the rotation fields. So again, this is a rotation around the vertical axis in here, and you can see those edge dislocations causing that rotation for that sense. Similarly for this sense. This is all driven by screw dislocations, much weaker because the screw dislocations, you tend to get some pairing of the sense of those to take out the long range.